Welcome everybody, welcome to the second day of our symposium. We very much hope you enjoyed the first day and were able to take advantage of the glorious weather that we've been having, so welcome. And it's great to see so many people here at 9 o'clock, so well done on that. And good to see that there's such interest in supply chain forecasting. When I first came to this symposium, which is actually I think back in 1994, supply chain wasn't particularly well represented, and it's become much better represented over the years, which obviously I am very pleased about. And I'm also very pleased to welcome our keynote speaker this morning, Professor Ruud Teunter, who is very much a leader in this field. Ruud is Professor of Operations Management at the University of Groningen, and he's worked in a number of areas: inventory optimization, the link between forecasting and inventory management, something which is very close to my heart, and also reverse logistics. And Ruud was very much ahead of the curve on this. He was looking and researching reverse logistics at a time when it wasn't fashionable. Of course, it is now. So if you'd like to know a little bit more about Ruud, obviously you can look him up on Google Scholar and you'll see that he's published lots of articles and you'll see he's got lots of citations, but that doesn't tell you everything. Because I think there's some things I'd like to point out about the importance of his work. Firstly, the impact on practice, that he's actually worked closely with some organizations and seen ideas translated through into reality. And both the elegance and intuition behind some of his results, but also a respect for robustness, making sure that these new approaches can work in practice. And I'm sure we'll hear more about that in his talk. I've actually known Ruud since I was just working out when I first met you, Ruud. I think it was in 1996 at the International Symposium on Inventories. And then Ruud was an early career researcher. And of course, he has developed his career to a very high point now, where he is a research leader. Just mention a couple of the accolades. Ruud is a past president of the International Society for Inventory Research, and he's currently an editor of the European Journal of Operational Research. So Ruud, it's our honor to have you as a keynote speaker. Welcome.
Yeah. Well, first of all, thank you, John, for having me, having invited me. And I would also say Robert, actually, right, because it started a couple of years ago. And then it was postponed a bit, this talk, because of Corona. So thank you for having me. It's fantastic to be here. And when you say leaders, I see you two and others as leaders as well. And I'm also very happy to see so much sort of interaction between supply chain and forecasting and so on. I think that is really important. I'll come back to that a little bit in a slide where I say a bit more as to how I came about to doing sort of forecasting and inventory control. I just put him on. Maybe you saw the little one as well yesterday, didn't you? Climbing the stairs and so on at lunch. It was really funny. You sort of can't read this, but on the placard actually says baby forecaster, which I think Pam did, which is sort of a great. So she's the next generation of British Greek forecasters, I guess, right? Which is good and scary at the same time. That was good. I put this on also. Aris was about to introduce me. You had to go back for anyone who wants to talk to Aris at some point. He's coming back later and staying with us for the rest of the conference. So we'll be back. He just had to go back for a personal matter. I'll come back to Aris. He's sort of part of the story as to how I ended up doing what I'm actually doing. So before I sort of, how do I come into this? It's certainly not that I was the one to point out that forecasting and inventory management should go together. I remember also I was taught, if you had an inventory control lessons before, you may have had the same book by Silver. I think it was Silver, Pike and Peterson there. It was even others. It changes. Silver was always there at Silver. I met him. He was a wonderful man. He was also really practical and did a lot of case studies. I think that's why Ed actually also said that it's sort of not straightforward to have forecasting and inventory and do them sequentially. You actually have to think about how the one affects the other and look at them together. He was one of those. But then actually I think I've got a quote of John and Aris said something. So over the time people have said this. So what about me? And I think one of the interesting things in the Netherlands is they have a study program which is not just management science, are not just econometrics, but it's both together. So more or less, as a study, I did econometrics, statistics, and decision science, which is one combined study, which I think is in a way quite unique. Many countries have either the one or the other. Even when I did my studies, I thought it was a little bit odd, because I had all this stuff on forecasting and ARIMA and all these models, and none of these teachers ever talked about, what is it used for? What is it used for? But then when I had actually my decision science lectures, it was a bit of inventory control, and people would say, okay, let's assume demand per week is normal, with mean 100, right? And standard deviation 20. Okay. That's also how a textbook on decision science starts, right? That's really odd. Because in that whole process, we forget, of course, that there's 120. These are forecasts. And certainly that matters, because we don't know what they are. We just have forecasts, sometimes good ones, but sometimes poor ones. How does that affect the decisions? So already there are sometimes in my study, it's like odd. Why don't we have combined courses rather than all these separate courses? To some extent that makes sense, to some extent that didn't. So I went on to do a PhD on inventory control. Why? Well, to be honest, it was the only position available. At the time, actually, I had done something very theoretical about traveling salesman problems, routing, everything known. And I liked it. I thought, okay, let's become a PhD. There was only one position, it was in inventory control. And I had a mathematics person guiding me. He said, okay, you do complex models. But I also had someone who actually was a mathematician, but had gone on to be much more of an operation management person. And he actually said, you go off to a couple firms. And you actually look at it, look at what's going on. And I went to a few, and I mentioned Philips here. And so what happened is I went to Philips, I stayed for 6 months. And my job is to produce forecasts, basically. Why? Well, they sell lots of stuff. Well, most of it actually is sold to China now, but they used to have everything in hand and do it in Europe and the Netherlands. One of the things, they sold televisions. And when they sold televisions, of course, they also provided service for those televisions. And they did so normally for at least 8 years. However, 1 year in, after they stopped producing, typically the spare parts people would say, okay, but you're no longer producing the television, so your demand is not so large. So make one last final buy. You have one more opportunity to buy these parts. And then you have to buy them for the next 8 years, right? So here I was, okay. So my job somehow is to forecast the demand for the next 7-8 years. Now this actually had been done by a few people. One of them was called Leonard Fortuyn, and he was still there. I worked together with him a little bit, but not many since. And I thought that's odd, because that must be a big problem. And since then, actually, some people have picked it up. The odd thing was, when I looked at Philips, which is a highly technically developed company, right? I actually looked for the data. They didn't have much. So I went to this computer. I remember they had 3 years of data, but only the last year was per month. So they had monthly data for the last year, and then 2-month numbers from 2 and 3 years ago aggregated over the year. So I went up to them, you want me to produce forecasts for the next 8 years? But I've got a demand history for 1 year, really. How does that work? And that actually, the story is, but they had microfiche. You remember that? You've seen the film movies maybe where people go to look at libraries to watch news clippings, and they put this stuff under the thing. Maybe the youngsters on the unit think, what is he talking about, right? This is ridiculous. But that happens, and you slide one under, you slide another one under. That's how they were storing their data, which is amazing, because 3 years ago they invented the CD, right? And when I asked them, why is it not in CDs, they honestly told me, do you know how expensive that is? So they had it on microfiche. Anyhow, I started doing that, and I couldn't really figure it out. I came up with some forecasts and some decisions. That was really difficult. Then I actually went to Lancaster later in my career, and I worked in the group of Robert, which is now your group, or your Together group. And again, one of the first things I came about when I worked with a student in a company is the REF case study. Some of you will know that because I've shared the data later, and quite a few of you have worked with this data set. And again, that was slow-moving demand, right? So slow-moving, I was into spare parts at the time. And what you have with these spare parts, they're not demanded so often. And so if you look even at monthly demand, you have a lot of zeros and sometimes positives. And I started working with that. And that's actually one of the stories I'm going to tell you about. So I've got 4 parts later on of my presentation, separate ones that I'm going to discuss. So this is the first, the RF project. And before I do, so the good news is I've got 4 parts. They're somehow linked, but also separate. So we can't really run out of time, right? Because I can stop with any of them. Also, right, if you've got your mobile, whatever out, you've got stuff to do, it's early in the morning. When you see a new slide, right, a new bit stops, right? So if you go off for a bit in between. That makes sense. Okay, so here's the first, and this is this case. I've also picked these sort of because with all of them, the story is not finished. I think there's a lot of research still left to do. So especially senior younger people, your PhDs in the room, I think all of these topics I'll point out why it is not sorted yet. So there is one demand, and you've actually maybe seen the picture in a data set by other people, because it's sort of become an iconic thing almost about the slow-moving part. This is a part of a 4 years which has 5 demands. And I remember at the time I was looking at this with Laura, who was a master's student, who went to do something completely different, by the way. She went to set up opera theater in some way, which is good because she loved doing that. But she was a really bright student. We started looking at this. And we said, okay, what can we do? And of course, I looked more and more at the literature of this sort of stuff. And one thing amazed me somehow, that everybody was looking at lots of forecasting procedures, like exponential smoothing, cross and more complex stuff. And typically, they were looking at MSC. So not at the relevance of the decision, not about infinity control, but purely at the accuracy, basically, of the forecasting. And then I said one thing, I said, okay, and certainly maybe I wasn't the first to do so, I said, but that doesn't show us the whole picture. So let's do a study for our data set with the same stuff, but I'm going to include one more forecasting procedure, zero forecast. Because when you just saw the picture, most of the time, it is zero, right? So that makes perfect sense. If probably you forecast zero all along, all the time, probably that works well. And it does, right? It works better than any of the others. It's a silly forecasting procedure, I'll tell you that, but it works better than any of the others. In this case, maybe not always, in this case, when you only look at the accuracy. Is it useful for a planner? Of course not. Because the planner will sit there, and if you use a zero forecast, what's the inventory decision? Don't stock anything, which actually means every time there is a demand, you're out of stock, things are late. So it is not useful. But this just goes to show that never look just at accuracy. Certainly from a decision perspective, that does not make sense. You have to look at other things. And then I said, okay, so look at decision implications, in my case, inventory implications. Now here's the downside. Also the downside when you submit something to a journal, I've been there, was once you look at inventory implications, you look at a specific system. And every reviewer can say, yeah, what you're showing is for that system. What about a different system? Which is true. I haven't then shown it for the different system. Still, I think it's important to do this, but you have to be careful in selecting your system. So for this one, we chose a really simple system. So there was discrete time. I'll get back to this. So discrete periods, like weekly or monthly data. I think in this case, we had monthly data also. That's what we work with. By the way, interestingly, REF at the time when we came there, they had over 1 million different SKUs. If I remember correctly, a value of something like 500 million pounds. And all 1 million SKUs were forecasted using exponential smoothing. Probably with a 0.2 smoothing rate. Everything. Which doesn't make sense at all, because it was all intermittent. But that's what they were doing. So the good news is we could, hopefully, I don't know if they're still doing it, but we could show that you could actually do clever things. In my system, so discrete time, the lead time is fixed. We'll get back to that at some point, right? So that means if I order something, it arrives 4 months later. Not stochastic, fixed. Back ordering of demand. It's a good point, by the way. If you look at inventory control, sometimes you make a model, there's 2 big options. Either you assume everyone is willing to wait, which is wholly unpractical, very nicely theoretical, right? Which is also why almost everybody assumes that this is the case. Everybody's willing to wait. So here I do. If you don't, you call it lost sales typically. So you lose the salespeople who are not willing to wait. I assume everybody waits. And I have the simplest of policies, which is the base stock policy. What is that policy? Every month, order up to 11. Well, or 20 or whatever. But you always order up to the same number. So if you have a demand for 4, you order 4 back. It's the simplest system you can imagine. Also, it's a system that makes a lot of sense in the spare parts world, in the slow-moving world. You don't need batching often, right? Because you only order now and then, twice a year, and then you order up to the same level. Okay. And finally, this is important, because also I was amazed sort of when I started inventory, I look at the textbook, 99% of this theory is based on a pure cost approach. What does that mean? We know the cost of keeping something on the shelf, but we also know the cost of servicing somebody late, which doesn't make sense, right, if you think about it. What's the cost of serving somebody late? Especially if he or she is willing to wait. This is an artificial cost. So why do people do that? Because it's theoretically nice, and if you have one cost function to differentiate, you take the optimal. It's easy, right? It's easier than optimizing under a constraint. That is more practical. So here's a constraint. And typically, if you want to do a realistic study, I think you have to do so. There's typically a service level constraint. Like I want to service 95% of the customers on time. Okay, so a very simple system. So we looked at that, and so what did we do? We did the traditional thing, and I'll get back to that in a few moments. So what's the traditional thing? You look back over time, and what do you forecast? The average demand per period, per month. And I call that mu, right? That's just the average demand. But then obviously also the forecast error matters, right? So you go for your best forecasting procedure, whatever it is. In this case, we'll use a moving average, so something very simple over time. And then you make the forecast, but you evaluate how good they are by looking at the mean square error. So you just look at the squared errors. Take the square of that as you always do. And that is your variance, the forecasting variance. And then what do? Well, then it's very well known that if you have that, what is this optimal order up to level? So you could be 11, could be 20. Actually, what makes sense is actually that you need to stock average demand that you have for the next 5 weeks. And I also realize I've written here this mu hat, which is for one period. So actually, there's a mistake. It should be L times there, right? If you have 5 weeks, your forecast per week is 5. Your lead time is 5. You need to store at least 5 times 5. So whatever this lead time is times the demand per period, plus this forecasting error. Well, and then you typically the textbook assume that forecasting errors are independent over time. And so the variance add up. So the variance is L times whatever the sigma squared is, and you take the square root. You end up with the square root of L times that. Oh, okay. Let's just do that, right? And now we can do that for all the methods that I had, all 5, and see how well they do. And so I typically do 2 things, and I think if you go to inventory control, that's important. I think really if you want to do a study and you want to look at the inventory consequences, there's 2 main things. In the middle, I'll say, okay, if I target 95%, what do I get? Well, I want to get 95%, right? But I should check that. If I target 95%, I get only 89, it's not so good. I get 99, it's also not good. That sounds good, but it means it's very expensive, right? To get the 99%. If I want 95, that's the second. But then other than that, what you of course always want is to get the best efficient point, the best value for your money. So if I invest a certain amount of inventory, for that I want the highest possible service level. So the second thing is to make this trade-off curve of inventory against service level. And you see that here. So what you here see actually is on the x-axis, I have the inventory level, and on the y is the service I achieved. And these lines are just all my forecasting methods, the 5 I discussed before. A bit unfortunate, they're all almost on top of each other, right? What does that mean? They're all equally efficient, which is not so good, right? Now I'm doing the forecasting, it doesn't really matter. Not quite though. If you look carefully, you see that the dark one, which is actually the zero focus one, is at the bottom, which means that gives you the lowest service level per investment. So luckily, it does show us the zero forecast, which also doesn't make sense. It's also the worst. But also it doesn't matter so much. If you do a study like this, don't worry. This is expected. Why is it expected? Well, think about my policy. What a policy do I have? I'd order up to some level every time. There's only one parameter, only one switch I can turn. If I turn it up, there's a better service. If I turn it down, there's a lower service. The only thing the forecasting does is tells me how I should turn the dial. But I can't change the dial. It's not like I have 2 dials, I turn this one up and the other one down. So because I look only at a very simple policy of one parameter, it's quite natural that whatever you do, even poor forecast, you don't end up at the right target, but you do end up with somehow an efficient solution. So don't only look at this, but do look at this, right? And then I say also look at actually how good you are at achieving the targets. Because at the end of the day, that's sort of the first thing you want to do. You want it to be accurate. And if it is accurate, and you look at the errors in the right way, what you expect is if you aim at 95%, you get 95%. Right. So this was also interesting for us. And it links to some of the rest of my talk. None of the methods was on target. They're all below target. I claim that all worldwide software and inventory control is wrong and produces below target service levels all the time. And I will tell you why in a minute. It's linked to later on. I'll show you a bit why this is. Because they make one sort of mistake, which is in part 2 of my story. I see people, I would just come in, there's lots of places in front and on the right as well. One thing that surprised me here is, and that also links to further research that we planned but never did, actually also with John and Ziad and Aris and others, is that even the bootstrapping is way too low. How can that be? Surely bootstrapping, right? L periods, L times the demand. I look at the mean of it, that must be spot on. How come even bootstrapping is wrong? And we looked at actually, we did bootstrapping wrong. But then it links to, I think most of the software gets bootstrapping wrong as well for intermittent demand. And I'll try to convince you why. So here's a pattern. And I hope you can see the color difference. There's blue dots and a red and a green one. The red and the green one are a positive demand. The blue dots, nothing happens, right? So with the blue dots, well, you can't see that the blue dots over there, the first 3, you just stick to S, right? And then a demand comes in, which is the red one, so you drop down. And you reorder exactly that amount. But it takes you, I think, in this case, 4 periods before it arrives. Okay. So what I hope is that it arrives on time. It arrives on time and nobody's waiting then. Well, think about it. When is nobody waiting then? So I have my S level. I drop down when I order, which is the positive demand. And then, right, in this case, I have another 0, another green demand, and another 0. And in it comes. What does that mean? That's sort of the total lead time demand is the red drop and the green drop and a couple of no drops at all. Okay, but that's different from what I just said. Because what does bootstrapping do? Bootstrapping looks at all these past demands and then L times picks one. So it could also pick L zeros, which is quite likely if you had 5 years with lots of, but think about it, doesn't make sense. Because what triggers an order? A positive demand. The red one, that's the one that triggers an order. It starts off the lead time. So the first draw must be positive. So we tried again and we said, no, don't just take L draws from what you've observed in the past as you do with Bootstrap. Take the first one only from the positive observations. And then the other L minus 1 could be positive or 0. You draw them from everything. That makes a big difference for intermittent demand. Because you don't have very many non-zeros. Forcing the first one to be positive makes a big difference. And this is interesting, I think, because it's also professional bootstrapping software used for intermittent demand. I think it doesn't do this. I think they just draw L times from all the demand. Doesn't make sense, but I think it's done. So we did, and we sort of said, okay, the solution is simple. We draw the first one from the positives and the other one, and then we compared. And it did actually work much better. Although, in hindsight, I think that it doesn't really show it from this picture, but the thing is, the axes have changed. Before they ran from 0.7 upwards, and now they go from 0.9 to 0.9. So things are looking much, much better, but not perfect. I'm still also below. And again, that also links a bit to the second part of my talk, which is about forecast errors being correlated and not independent. So there's a problem here. But already that's much better. So always think about the case, right? If you have intermittent demand, What is the lead time? What is going on? Now, interestingly, and then we said, okay, but that's just part of the story, right? But think about it. Why did I just say the lead time is the red drop and the green drop? Because I had this nice, simple policy, the simplest of policies that said, I'm always at the same line, and then I drop below. That is not the case in general. Typical policies are of the order level or the quantity type. So you have some order level, some typically called a reorder level, and if you drop 2 or below it, you typically drop below it, because demand, especially for spares, could be 5, 6 for 10 items at a time. Then you have what we call an undershoot. But the undershoot is not the whole demand, right? Because I'm above the order level and I drop below it. So only a part of that order is the undershoot. That's the part that is the initial bit I drop below. So if you think about bootstrapping, I can't just bootstrap one of the complete demands, because only part of that is my undershoot. How do you do that? How do you actually sort of do a bootstrapping procedure in general for an RQ policy, which is the most used policy, and I think to date is not done. So if you're looking out there for things to do, I think this is really one. Nobody knows how to do this, but it's super relevant. And this happens in software as well. Interestingly, in software, if you really dive in and you talk to the people and you look at the manuals, it doesn't really explain often what they're doing. I'll tell you later on, we tried a little bit to find out what they did, and often we couldn't. We couldn't find exactly out what they were doing. Okay. Good. That was the first bit, sort of the first story. And I already hinted at this, right? So there's still a problem. I'm still below. And that links to forecast errors being correlated. Always, and I think always is the thing to stress here. So for each one also, I've put a thing on so you can look back if you wanted, read back at what we did, what we didn't do. Maybe even more so if you're a junior researcher. So here's my statement. Maybe the first statement is the most important. Forecast errors are always correlated, even if demand is not. Right? Again, I take my inventory textbooks and they say, okay, let's assume demand, normal, 120, independent over time. It doesn't make sense. Well, it does make sense, but I need to realize that the 120 are just estimates. What I'm telling you is because they are estimates, you have to immediately drop the assumptions that the demand is not correlated. That cannot be. I'd even before you show you a little bit of math, think about it. If I make a forecast, and let's suppose the real mean is 100, but I forecasted 95, but it's 100 for the next 5 periods, and the lead time is 5, then I'm 5 times too low. I can't be 2 times too low and 3 times too high. I am 5 times too low. It's 100% correlated. So if you think about the forecast error, they must be correlated. Even if the demand is perfectly stationary, independent over time with the mean 100, forecast error is not. It's the same for all these periods. So remember what I just said to you with how do you set typically safety stocks? You take L times this one-time ahead forecast, L times, assuming independence, which is why you get the square root in. What I'm saying now is don't do that, right? If you ever did that, you have software, stop doing that, because it's not the right thing. And then here, we did this for a small study, and we showed that it matters, right? It's not a small difference. It's a big difference. Luckily, here's one of the things, because it's very seldom, I must admit, if you do things that is picked up. But at least I know that a couple of software companies adapted their software, and they are using slightly higher safety stocks now. But the story is not finished, because I'm only going to do this for a very simple model, and it has not yet been done for the more complex ones. This is just to show you also that there's also the problem with the undershoot, right? If I combine the problem with the undershoot with the correlated forecast, the story gets modeled. So here I don't. I forgot about the undershoot, right? We just look at, you hit R exactly, you have L periods ahead, what should you do? So even this is not the complete story, but I did so to bring my story across. Even in the simplest case, you don't have the undershoot, you just have L periods. I just want to look at the fact that things are correlated. Right. So discrete demand again, discrete time, and I'll get to this in my next story. So why is it discrete all the time, right? Is inventory control discrete in practice? No, of course it's not. It's continuous or almost continuous. You can order it every time, certainly nowadays. But okay, for now, let's stick to speed periods. Demand is normally distributed. How do I know that? Perfect insight, right? No, for the story. Doesn't make sense. Again, that's a point for a later extension. But for now, I know it's normal. There's a fixed lead time. I have this RQ policy, some batch queue. And again, I want to have this target service level that I focus on. So it's a very simple model again. Okay, so let's look, and again, what I just said in words, like if you're too low, you're always too low. Let's just put this down mathematically. So if I look at my forecast error over the lead time period, over my L periods, what I get obviously is that I need to look at the whole demand, lead time demand, which is simply the sum of the future demands, minus L times my forecast per period. Well, that's it. Then of course I can easily split that out. Because that's like the same as the real minus the real mean, plus the difference of the real mean and the estimate that I have. And now you directly see the problem. Because look at the variance of this. And now this first term on the left, that's a nice term, right? There's just the y's with a real mean. So the variance of that thing is just L times the variance. They're independent. But the bit on the right, it is L times the same thing. So surely the variance of that, as we all know, is simply L squared times the variance of the latter bit. And you get that. So here the key thing is the L squared term. It's not L times. Yes, it's L times the variance of the demand, but it's L squared times for the forecast error. Okay. So interesting, we thought. Interestingly, not all editors thought. And I remember one thing actually is that, and this is what we didn't do this initially. So we had the proper thing, right, which is L squared, and we know what the textbook says. And the textbook basically says use L times the variance. And then you think about it, use L times the forecast error. But actually, I think we sent it into POM at the time because we thought it was practical and sort of OR and solid. And the editor said, I couldn't care. Why don't you worry about the focus error at all? Just put in the demand. To me, that didn't make sense. But we just put it in additionally as well. And in the hindsight, he still didn't like it, but we said that's sort of a very naive approach. Just forget about forecast errors, right? That's what you can do. Okay, so we did. And then we also had the second method, and that is the method I showed you before. So basically what you do is you take L times the forecast error, which is L times the square root, the MSE. And the MSE is known to be for one period ahead, which is recommended, right? One period ahead, you get the demand variance plus the forecast variance. One time, because it's one period. And then you just do that 5 times, so times 5. So still wrong, but it makes more sense. So in the end, what do we expect? Well, if you underestimate the variance, you're going to have too low safety stocks, too low service, and so on. Right? That's what you expect. So again, just to remind you, what are we looking at? We're plugging in a traditional formula for inventory control. To please, so the proper thing is on top. It has this L squared term. Then an naive approach is to completely forget about forecast variance. And the middle approach is the usual approach. Because the usual approach is look at the one-time head forecast error, and you can easily show that what you end up doing is having an L instead of L squared. Because basically you ignore that forecast errors are correlated. And of course the key thing, it doesn't matter. And you get these results. So we see the correct approach here, and that's at the top there, the highest one. So actually that says that it should be way higher, right? Well, what is on the axis here is the number of observations. If you look at the right, it doesn't really matter. What is on the right here? I have a moving average with 52 observations. So if I use a moving average, I've got, say, 50 plus observations. Stop worrying. You can do any of them because there hardly is any focus variance. If you work with companies, you know they never have 52 good forecasts. Most I've seen use 10 or 12. 10 or 12 weeks. Sometimes they use even 4. Depends a bit on And here's again, for me, the interesting thing between theory and practice. When I studied econometrics, I was also told, let us assume that demand follows an AL1 process. And if we took 2 hours to derive the best estimator, how did they ever know it was an AL1 process? Why is it not a completely stationary or non-stationary process? It could be anything. That's actually why in all of these competitions, ES does so well. Because ES is just very robust. Hardly ever optimal, but it's okay for all of these. So you basically don't know what's going on. So if you have, say, up to 20, 30 forecasts, it really matters. Maybe more telling, actually, if you look at the service that you get by doing this. And what you see is that our corrected methods, it aims at 95, it gets exactly 95. Sort of in the long run. But the others don't. And they are way below, right? So the middle one, I would say, and the bottom one, both, this is what is in the software worldwide. So what we see is up to, what is it, up to maybe 20 observations? You're way below the service level that you want to have. Yes, if you have very many good observations, you're fine, but otherwise don't, right? You're going to be way too low. It doesn't work. And then, I'm not going to show you the results, and even skipped over this, because what did we do in this first bit? I said, we know it's normal. We know it's normal. We don't know the mean, but we do know the standard deviation. That doesn't make sense, right? How can you know? But because we could make the nice, easy analysis because of it. So the next step is to say, okay, we also don't know what sigma is. We need to estimate it. Do the same thing, but instead of a normal, you have a t-distribution, sort of basic statistics. We lent some stuff from somebody else in the past, and we basically got the same results, the same errors. But now we're estimating, or even slightly higher, because now we're estimating sigma as well, and sigma has also got a forecast error in it that you should not ignore. So we did a little thing there. But then there's lots of stuff we didn't do. Like how do I know it's normal? I don't. So I am still, when I say correct, I'm hitting exactly 95. I'm only hitting correct because it is exactly normal. I just don't know the parameters. What if it's not normal? That is an extra layer of uncertainty. But somehow you need to incorporate and must lead to higher service levels. Or to too low service levels, to higher order opti levels. So how to do that? And that is not known. So again, that leaves a lot of room for further research. What about the demand? My demand. And there was a mismatch there, and it's always difficult to sell. I looked at stationary demand, right? But not having so much of it. So I still took a moving average. Because honestly, if you got stationary demand, you could just over time have the perfect data. Makes more sense maybe to look at non-stationary demand. And a few people have started doing that, but it's really tough to get some hard results out, right? Which you know is also the difficulty in publishing sometimes, because actually the UR journals are sort of fixated on sometimes having very hard results, rather than, I think, intuitive numerical relevance. Demand could be autocorrelated. What about the lead time? Is the lead time ever fixed? Sometimes it is, in many cases it's not. And it's unknown. You also need to estimate the lead time. And you're going to have an estimated variance. What about that one? It also, somehow, all of that needs to be incorporated. And that's not done. So I think there is lots of future research there ahead. Also realize that maybe I should have done with the first one as well, because this is sort of the end of the second bit. Of course, I'm willing anytime you want to take questions. So if you have specific questions about this bit, you can take them now, just raise your hand. Otherwise, I'm going to go to the third bit. No? Okay. And that may be the last bit when I look at the clock. To me, that's sort of interesting as well. You think about it, because what I know mostly of forecasting, and I said that before, is it's discrete. It's per week. Companies do it per week, or per month, or per day. The forecasting isn't. The decision control isn't, certainly nowadays. Well, sometimes there's a few firms that ought to say always on a Monday. But typically, they have these software systems, and whenever you hit a level, any point of the day, you place the order. So the inventory control is continuous time. But somehow, you have the discrete time forecast that need to fit into this. And we started looking at this, actually, again. We started looking at companies. And for my interest in intermittent demand, lots of zeros and positive, how are they doing this? To be honest, we couldn't figure it out. So some of these, they had these systems, With the continuous review, so for instance, like slow moving, like SQ policy, so when do we order? But how they set these service levels, and somebody were using Croston. Saw that, somebody were using Croston. So what does Croston do, right? Croston is, when you have these periods with zeros or not, basically does two things. It looks at the time between zeros, so the time to a demand, which is same as the probability of having a demand. And if you do have a demand, it forecasts the demand size. That makes perfect sense, because these are the two things that put together a slow-moving demand process. Only sometimes you have a demand, and when you do, it has a certain size. By the way, think back to the RAF, that is also what we introduced there. They were just using the average over time, like 3. Rather than saying, no, it's once every 4 months, and then the average height is 12, which is much more informative, right, for the planner. Okay, but how were they using Croston per month? And then somehow using this in a continuous setting. Because in a continuous setting, there is no time period. So in a continuous setting, you need to know the process, the demand process. And the underlying process, the most normal, is a Poisson process. Right? You have an arrival rate continuously over time. And then when something happens, yes, you have a certain size of the demand. But think about it, even if you don't have that many demands, if you pick 1 month, there might just by chance be 2 or 3 demands in it. And you lump them all together into one demand. What happens if you do that? You get a more lumpy process than a real process. If you put that more lumpy process into your inventory optimization, surely you're going to overhit your targets, because it's more lumpy than it really is. Looks more lumpy than it really is. So we looked at that. And we said, okay, can we not do something about that? And interesting, like I said, for the software packages, so we looked at packages, they use Croston, and they set the levels continuously, but we could not actually find how they do that. So we had to guess, because we wanted to say, okay, here's how they do it, here's how we're going to do it. We couldn't find out how they were doing it. It was not clear, and nobody could explain it to us. I had good contacts at one of the firms, but they couldn't explain it. Yeah, so that's basically my story here. Nobody could tell me what it was. And I think it's interesting, this is also hardly addressed, neither in the forecasting nor in the inventory control literature. So that at the end of the day, for many decisions, you need to work with continuous time forecast of the demand process itself. Not the accuracy of demand per time period, that is not directly relevant for decisions you want to take continuous time. And so I talked about Croston's method. What does it do, right, again? Looks at the time between demands, which is 1 divided the probability of demand and the size of demand. It uses twice exponential smoothing. So it's a very simple method. I guess many of you know it. And intuitively, what could you say if you have something not moving too many times, right? If you see 5 periods and you see a demand in 1 of the 5, a positive 1 or 2 out of the 5, you would say the arrival rate is 2/5. Because on average per period, 2/5 demands arrive. And so my lambda is 2/5. Here you see the problem, right? What if one of those positive periods had not 1 but 2 demands in, and actually there were 2 + 1, 3 demands? I should have gone for 3/5. It's just that I don't know. So how do you go back from the fact that you don't know to still estimating the proper lambda? It might be 2/5, might be something else. And it turns out that's actually not too difficult. So we tried and do that. We tried a different method of doing that. But before that, maybe, why are we doing this? We also checked, of course, whether just taking that slightly more lumpy process, putting it in, does that work? Does that give us the right service level? No, it overshoots like we expected. By how much? Well, that depends, right? If you look on the top, actually the overshoot, especially for the first columns, is not so big. And that makes sense, because there's a demand every 16 periods, 1/16. So the chance that things are lumped together is really small, right? Because that's like 1/16 maybe of the periods that it happens, not often. But if the lambda is 1, it means the average number of demands is 1 per period. It's almost not intermittent anymore. Then very often things are lumped together. If you ignore that, you're going to be way off. And you are going to be way off. You overestimate the lumpiness and you put this into your procedure, it's going to go wrong. The other way around, by the way. Now your service levels are going to be much too high. Okay, so what can you do? Well, just estimate them properly, right? Which is, you can do this properly. You just have you have the demand realizations. You know it's a Poisson process with lambda And then you need, of course, some compounding process, right? So we look at very simple compound. The compounding process is the size of the demand size. You need a distribution for that. And we looked at very simple ones with one parameter. Why? Because then we only need to estimate one thing. The size could also be normal with some mean mu and sigma, but then you need to estimate the mu and the sigma on top of the lambda. So it's another level of complication. So we never went there. We went to two simple ones, geometric and exponential, with one parameter. What could we do? Of course, we can use the method of moments. As I said, actually, interestingly, most books don't even mention this. But those that do, and actually is a really good infantry textbook. If you need to teach on infantry, I would recommend that book. Well, Sven is not with us. Well, we have a Sven, but Sven Exit is not with us anymore. It's still a really good textbook, I think, to use. So there's a method of moments. And then what you do typically, method of moments. So you look at all the periods that you have, and you look at the expectation of a demand in a period, and the expectation of the squared. That is strange if you think about it. What is my demand process? My demand process is sometimes I have a demand, sometimes zero, sometimes not. So the number of zeros will not tell me about that part. And then if I have a demand, I have a demand size. And I can look over the positive demands and I can calculate the average demand size. Surely it's best to use that to come up with the demand size and look at the number of zeros to look at how likely is it to get a non-zero. But the method of moments doesn't do that, the normal one. It looks instead not at the number of zeros, it looks at the average demands, including zeros and non-zeros, and the average squared demand. But we tried that as well. We also tried maximum likelihood, and this is why it was quite difficult to sell this paper, because in the end they said, why don't you just use maximum likelihood? And it does work, as well as what we are going to suggest. Our argument was that it's way more complicated. Actually, it wasn't even closed form for our thing, so we could only do it numerically. So what we say instead is actually, we use sort of an adaptive method of moments. And it's very straightforward. We look at the number of zeros, and we use that to determine our lambda. And I'll just show you how that works. So suppose we have n observations, right? So I have 20 observations. And 8 of them were 0. How many zeros do I expect? Well, in this case, let's assume that demand is, it's an exponential process, right? A Poisson process. So the first probability of having no zeros is e to the power minus lambda. So actually, e to the power minus lambda times the number of observations should be exactly the number of zeros that you observe. So we just plug that in. The expectation of the number of non-zeros is this. Then let's assume we observe n zeros, so that's the observation of the zeros. We just plug that in. Job done, we have lambda. And once we have lambda, it's very easy. You just take the lambda, you multiply it with the mean demand per observation. Because if you have lambda demands per time units, and each time they have a certain demand size, then that's your mean demand, and you just equate it to the real demand size. Note, I never need the second moment. That's the nice thing. I only need the first moment of the demand. So now the number of non-zeros is consistent. So it's sort of crossed then, continuous time. And then we compared it. And the nice thing is, like I said, without the pictures, it works as well as maximum likelihood, which is not closed form even for this simple case. And it's way better than the normal method of moments. So then we said, at least for this, it makes like a logical alternative. Also because the cross-sum method and this way of doing it is easy, right? If you talk to a manager, you're estimating the number of zeros and the size of it. It makes sort of perfect sense. So what we said is don't do this, separate them out. But, and again, this is for people out there in the audience, maybe, I just looked at a very simple case, right? What about other processes, other things, other difficulties? We didn't go there yet. Thank you, Tom.
Thank you, Ruud, and we have time for questions.
Ruud, perhaps I'm going to ask the obvious question. You presented a series of theoretical perspectives, but you started with the initial observation and how
Yeah, I think the one thing is that one thing which is changing, I think, is that what I've seen in many firms is that in many companies, there is no trained statisticians, first of all. And yesterday we talked about probabilities. And I remember actually that I once went to Van der Lande. I talked to them about inventory control, very basic things. And there was a team of 8 people, and they were controlling 20 or 30 millions of stocks. And not one of them had any training. Because I had a few slides on, and I said it's something to do with the variance, right? You have a safety stock to cover against demand uncertainty. And they directly asked, what do you mean with uncertainty? Once I mentioned variance, they were off. So one of the things is, and I think that is changing, because we're training a lot of people, and I see them ending up in supply chain as well now, and doing sort of better things. I also do think for that reason, like you said, that it needs to be really simple. So when we actually implemented a couple of things, typically from my work, it's not only this, but I also did some work at varying service level across a large number of SKUs. And what I found out is the things that worked are less optimal, but simpler. Maybe even simpler than this. So here I'm proving a point, but when you want to get it across, it needs to be. For me also that links a little bit to everybody's talking about, big data, big numbers and black boxes and so on. For more complex methods, will that change the future? Will that allow people to adopt more complex methods? And that I don't know either. But yes, I've been amazed sometimes by it. Maybe you also don't interact enough, right, with them to really get it done. I think you need to get it sit. So the things that I've implemented typically, they started out with student projects, and the students actually implemented a bit in the software, and then later on they modified it into the real software. But you need to sometimes actually sit with them and spend time, which is also something we do not do. Yeah, but it's a valid point. Why do even the simple things not get implemented all the time?
So really fascinating presentation. 2 comments. One is on the notion of reordering levels. In economics, this is something that's gotten a lot of attention, or got a lot of attention. There's a really interesting paper by George Akerlof, now a Nobel Prize for it, and Ross Milburn back in 1980, looking at exactly this issue for asset control or asset management, where the thresholds for changing allocation of the portfolio also depend upon longer run parameters that would be functions of the whole data generation process, which is quite important if the data generation process changes. So that's one reference that might provide some additional insights here. The second actually concerns changes, structural breaks, and in a sense, this is sort of ignoring or bringing to attention the elephant that's standing in the room. What happens when your supply chain disrupts? And that's not really been addressed here. And so it'd be very interesting to look at what sort of forecasting rules here are robust and are not robust to major changes in the whole data generation process. And of course, that's what we've experienced over the last 2 years. And it would be one of these items for further research, but it really does seem something very important to address. There's been a number of papers presented already at the conference on robust devices for forecasting.
Yes. No, good points, and I agree. And to me also, by the way, that's when I say that firms often use 4 or 10 or 12 at most data points. What you just said is basically the reason. Things change over time. Even this little major disruption, demand changes, the period changes. Things sometimes you have big interruptions. And so firms, they realize that they shouldn't look back too long. And they look at small periods. And so not a lot of demand. So dealing with a limited number of points. In your case, also deciding what to do, because the risk that comes with that, right? When do you look, when is there really a switch, and when to incorporate that in your forecasting or not? I think these are key issues. For the majority, I would also say to the people here, really looking at forecasting situation where you do not have much demand, that really matters, and things are non-stationary, is highly relevant. I see people often also looking at asymptotic properties. And I've been at cases where editors ask me, can't you prove asymptotically and I think, what's the relevance, right? If I have an infinite number of data points, yes, I'm going to do it. But that's not real life. The real life is I don't exactly have a limited number of data points, and I need to get something that works. So I agree. So that links a bit to your points, I think. But it's really complex to get out the non-stationarity, forecast it, and then somehow include it also in the decision side. That's really difficult.
All right, Ruud, thank you very much for a fascinating talk. One question in the very beginning of the first paper you presented, you said nobody knows their costs, so we're going to go with a target service level instead. And that to me kind of begs the question, how do we set the target service level? How do we decide whether we to go with a 90%, 95, 98, 99%? And that really depends on, well, what's the optimal one? And there you need some assumptions about what's my cost of underage, overage, or whatever.
Definitely.
And there you have your chicken egg problem. And so really the target service level that we work with too, it's really Puma, right? It's pulled out of my whatever. And that kind of, and if your target service level is so uncertainly defined, it's so hard to really pin down what the target service level is, then, well, my stupid question to you is, how important is it whether we really achieve it or get 0.2% below or 1% above that? Any thoughts on that?
Yeah, well, first of all, I think you're right. If you are sort of with the half a point of that, it was sort of set in a soft way anyway. So that's why I also said, so by the way, always look at the achieving target and the efficiency. So at the very least, you would then want a method that gives you whatever you have at the best cost, at the lowest cost. So there shouldn't be something else that gives you the same service level at half the cost. So in general, we say always do both, but I agree with you. You get close to it, how do you set the service? In practice, it's often just a manager saying that's what we want. That's what we aim for. And if you go into why is that what you want, I've done it sometimes, especially when they want something really high, like 99% across all the SKUs. And then I explain to them that theoretically, because 99% is 1 in 100, you can actually show that's like a 1 in 100 right. So the penalty cost for not having is 100 times holding it. Is that really what you want? And then they say, well, it's not that bad, so maybe then you shouldn't go for 99. So sometimes we have that, but it's a difficult discussion. But I agree with you, basically, if you get anything that's sort of in the range you really want to be in, plus it's efficient, so there's nothing really better than that, you're a happy person. And stop right there and go with that.
Can we just thank Ruud once again for a fascinating talk? Thank you.
Thank you.